Spin is everywhere. The small magnetic moments, the spins, enable many modern devices in our daily life. And these range from smartphones to electromobility, from medical diagnostics to the electric guitar. Magnetism is found naturally in minerals like magnetite, and this was known in ancient times in Greece and also in China, where magnetite was used as a compass. Spins are a fascinating topic with academically exciting new findings coming out daily. And at the same time, spins enable new applications.
Spins are the fundamental constituents of magnetic materials, and magnetism is a core part of the curricula in subjects ranging from physics to materials science and electrical engineering. Students learn about the fundamental details of the quantum mechanical spin, which is important in many fields, from chemical reactions and quantum technologies to the applied development of disruptive new magnetic devices.
At the center of the rectangle.
One type of magnetic device that is found all around us is the magnetic sensor. For instance, dozens of these sensors are used in every modern car. Magnetic sensors precisely identify the location of the magnet. If the magnet is attached to the shaft of a motor, the sensor can precisely read the speed of rotation. One of the discoveries which has revolutionized modern sensors and digital data storage devices is the giant magnetoresistance effect. Imagine two permanent magnets separated by a non-magnetic metal such as copper. Let's say we're able to fix the magnetic orientation of the lower layer such that its magnetization always points towards a certain direction. If we then switch the orientation of the top layer, it was found that there is a giant change in the resistivity across these layers. This allows for detecting even small magnetic fields, which makes the modern magnetic sensors highly sensitive. To fabricate these high-quality ultra-thin layer stacks, sputtering is used. Using sputtering, we can deposit just a few nanometers of high-quality material, for example magnetoresistive multilayers, on top of silicon wafers. In modern fabrication machines, the process can be fully automated for scalability and reproducibility. The thin layers will be structured into well-defined nanoscale elements using lithography techniques. To reduce the risk of contamination during processing, all of this has to happen in very clean environments known as clean rooms. In addition to sensors, we can also make devices for information technology. Why do we need to make better, faster, and more efficient magnetic devices? Because we produce more than 11 trillion bytes per second all over the world.
This is a hard disk of your computer, what you use every day to store your emails, your photos, your movies, or even your information on clouds. The basic idea to save one bit of information is very simple. We use a so-called magnetic domain, which can be magnetized in two different directions. If it's magnetized like this, it's a logic 0. If in another direction, then it's a logic 1. Now, if we have billions of such domains, we can store any information, for example your movie. The question is how we can switch the magnetization from one direction to another. The latest generation of hard disks, so-called hammer systems, use short laser pulses to do the job in the presence of a weak magnetic field. But can we do it faster? Here in our laboratory we explore what is the maximum switching speed for a magnetic domain. And to do that we use the shortest laser pulses which are available nowadays.
Our lasers generate laser pulses with only 10 femtoseconds pulse duration. This is really short. The light, which, as we know, travels with the maximum speed possible, makes in 10 femtoseconds only a distance which is smaller than the diameter of a human hair.
Scientists send these laser pulses to a magnetic sample and measure how fast it switches its magnetization direction using a spin analyzer. By moving the laser beam, even the switching of arbitrary patterns can be achieved. The fundamental limitation of the speed of the data storage is still an open question, but the researchers know that it can be at least 1,000 times faster than the currently available technology.
Magnetism is indeed great for data storage, but over the last years physicists have realized that it is also good for data processing. We do need to search for new types of computers, and the idea is to use magnetic waves, so-called spin waves, and their quantum magnons to process data.
The red arrows on this screen represent the magnetization as for data storage. However, for logic output only slightly tilted. The magnetization will start to rotate, and this motion spreads in the form of a wave, which scientists call a spin wave. This then transports information for low-power data processing. And this is just the beginning. Demonstrators have been developed in various labs around the world. Now the task is to make them smaller and faster, and to combine many spin wave logic units into a single chip.
We face a major global challenge. We need to transform our society to renewable energy technologies. In order to develop these technologies, we depend on critical raw materials. These are strategic elements such as rare earth elements, but also cobalt and lithium. In short, the energy transition is the materials transition. This is particularly true for high-performance permanent magnets, but also for magnets for magnetic refrigeration.
In order to make a high-performance magnet for energy applications, one needs to identify new intermetallic compounds with excellent intrinsic magnetic properties. The elements are mixed with each other in an arc melter to form the right phase with the right crystal structure. Then the next step is to process this pre-alloy by rapid quenching in a melt spinner into a nanocrystalline material. The liquid metal is cooled down by 1 million Kelvin per second when it hits the copper wheel. The rapidly quenched powder is finally hot pressed into a fully dense and highly textured bulk magnet. This can go straight into the application. Key applications include electromobility. In mobility and transportation, electromotors will replace the traditional combustion engine. High-performance magnetic materials, both hard and soft, make these motors small, light and efficient. Their generated torque scales with the remnant magnetization of the rare earth permanent magnet. In modern direct drive wind turbines, again, permanent magnets are used to make the generator small, efficient and robust for difficult to reach offshore locations. For 1 megawatt produced, we use half a ton of magnets, and 30% of this weight is rare earth elements. Magnetic systems also contribute to marine animal conservation efforts by monitoring animal behavior. And magnetic resonance imaging is widely used for medical diagnostics, allowing one to obtain images through the solid body to detect pathological conditions such as cancer, stroke, cardiovascular or neurological diseases, among others. In current preclinical research, imaging is being combined with nanotechnology, enabling the development of novel diagnostic strategies through magnetic nanomaterials used to generate increased image contrast. Spin is everywhere. It combines exciting science and possible pervasive and ubiquitous applications from sensors to low-power information technology memory and logic. Furthermore, spin enables electromobility and green power generation.